Hello everyone. In this video, I will go over my solution for the problem named almost all multiples taken from Sarang's round. This problem is an excellent problem which will teach you how to use the prime factorization of a number to implicitly find cycles in an array. So in this problem, we are basically given two integers n and x and a permutation of length n. We want to print a permutation of length n which satisfies the condition that Pn is 1, P1 is x, and the permutation is the lexicographically minimal such permutation. So we want to find the minimum such permutation among all permutations that satisfy the condition that Pn is 1, P1 is x, and I divides Pi for all I between 1 and n minus 1. So obviously 1 will divide any number. So we can see that 1 divides x, and this condition is met for I is 1. So we need to ensure that for all I going from 2 till n minus 1, I divides Pi, or Pi is a multiple of I. And we need to print the minimum such permutation if it exists. If it doesn't exist, we need to print minus 1. So for example, if we have 3 comma 3, which basically means that Pn is P1 is 3. So and we know that P3 is 3, P3 is 1, sorry. So the only possibility left is for P2 is equal to 2. So that's why it's obvious that the only permutation is 3 to 1, and that permutation meets the conditions that 2 divides 2 and 3 and 1 divides 3, because we only need to go till n minus 1. We don't need to check n, because obviously if you check n, there's no way that n divides 1, because n is not equal to 1. For n greater than or equal to 2, we know that n is greater than 1, so n cannot divide 1. And that's why we don't need to check the nth position. We only need to check from 2 till n minus 1. In the next example, when n is 4 and x is 2, let's write it down over here. So we are given that n is 4 and x is 2. So this means that p of 4 is equal to 1. So if we fill in the array of 4 elements, then we know that p of 1 is x and p of 4 is 1. So this is the array, and we want to fill in these two elements. So in order to find, there are obviously only two possibilities, 3 and 4 or 4 and 3. So 4 and 3 doesn't work because 2 does not divide 3 and 3 does not divide 4. So we need to ensure that 2 divides 4 and 3 divides 3. So that's why the only possibility is 2, 4, 3, 1. This is the only possible array, and this is also the minimum array. And that's why we print 2, 4, 3, 1. Note that we need to find the minimum array among all possible arrays. So if there's only one array, obviously we'll just print the single array, which is the case in the first two examples. And if there are no arrays, we'll print minus 1. And that's why the output is minus 1 for the last example, and the output is the single such array for these two examples. However, there can be other examples where there are more than one possible permutations which you can print, and let me show you an example of that. Because in those examples, we need to come up with some logic using some prime factorizations. So I'll be explaining that in a bit. So let's take an example. So if we consider the example when n is 12 and x is 3, you'll notice that there are a couple of possibilities. And this example will actually help us build the full solution. So we'll start by going backwards from n till 1, because we know that if I should divide p of I for all I going from 2 till n minus 1, because obviously this satisfied for I is 1, we know that n minus 1 will be the most restrictive, because p of n minus 1 should be equal to n minus 1. Like, we can conclude this straight away, because if p of n minus 1 should be a multiple of n minus 1, there is only one multiple of n minus 1, which is less than n, because this is a permutation. We want to ensure that like all the numbers get swapped appropriately. So we want to ensure that all the numbers belong from 1 to n, and each number comes exactly once, which is why it's very easy to conclude that p of n minus 1 is n minus 1, and p of n minus 2 can also be n minus 2 in most cases, and so on. So we can fix the elements from the end. But we cannot easily conclude that P of 2 is equal to 2 or P of 3 is equal to 3. It's possible that P of 3 is not equal to 3 in this example. There is one possible case in which P of 3 is not equal to 3. I mean, because uh, because we know that x is 3 means that this should come here. We know that as a fact, P of 1 is equal to x. That's given in the problem statement. P of 1 is equal to x. So we know that P of 3 cannot be equal to 3. And that's why uh, we know that at the position 3, some other number should come. So it's easier if you go backwards from n till 1. So if you consider the position n, we know that P of n should be equal to 1 because that's what's given in the problem statement. And we know that P of 1 should be equal to x. And we need to fill in all these places. Now using the logic which I just said, P of 11 should be equal to 11 because there's only one multiple of 11 which is less than 12. So we put 11 there. Again, we put 10 over here, we put 9 over here, we put 8 over here, we put 7 over here. Because again, there are no multiples of 7, there are no multiples of 8, there are no multiples of 9, there are no multiples of 10. The only multiples are the numbers themselves. However, at the position 6, we have two possibilities. We can put either 6 or 12 because 6 into 1 or 6 into 2 are the two multiples. Position 5 is again fixed, position 4 is again fixed because if you put 8 over here and if you put 4 over there, it doesn't work because 8 is already taken, so you have to put 4 over here. And at position 3, you have a couple of possibilities. If you put 12 over here, then you can put 6 over here. And if you haven't put 12 over there, if you have put 6 over there, then you can put 6 over here. So, I mean, then you have to put 12 over here. So I'll explain the two cases, but for now, notice that all the other positions are fixed other than 3 and 6. So, and 3 and 6 are the only two positions which are not fixed and which can be 6 or 12 in this order. So we know that if P of 6 is equal to 6, this means that P of 3 is equal to 12. Otherwise, P of 6 is equal to 12 and P of 3 is equal to 6. So out of these two possible cases, we know that the second case is more optimal. The second case is lexicographically minimal because we have a smaller value of P of 3. And notice that lexicographically minimal basically means that we have to minimize the smaller positions. So we need to minimize P of 3 instead of minimizing P of 6 because P of 3 comes before P of 6 in the array. So that's why we choose case 2. So this means that we set P of 6 to be equal to 12 and we set P of 3 to be equal to 6. And now you'll notice some pattern happening. You'll notice that 3 times 2 is 6 and 6 times 2 is 12, and this is going to be the basis of the full solution, that you figure out some property of multiples. So I'll be explaining exactly how we go to that property, but for now just notice that we are concerned only with the positions which are not fixed. The positions which are fixed are the positions like 2, 4, 5, 7, 8, 9, 10, 11, which can't change because there are no multiples of that number. Only the positions which are a factor of n and are a multiple of x, only those can change. And I'll be explaining exactly how to find out the numbers which should come at those positions. So to make this clear, let's take another example of x is 2 and n is 54. So in this case, as I mentioned, the numbers which are multiples of x and factors of n are the only ones which will matter. So let's make this concrete. Let's say that when n is 54 and x is 2, we know that P of 54 is fixed to be equal to 1. And we know that because of this, 54 needs to come to one of the positions. So we need to make P of some number k equal to 54, which is n, some P of k equal to n. And since P of 1 is equal to x, we also need to put some, we also need to make sure x divides p of x, and where p of x is not equal to x. So if you consider these two cases, if you consider both of these conditions, you will realize that one simple possibility, one simple construction is to just put n at the position of x, because we need to put the number n and we need to fill the position x. So the number n is free, so x is the position and n is the number. So since the number n is free and the position x is free, we can directly put the number x in this position, and that is what happens. That is case one in the previous example. But as we noticed, there was a cleverer way of of moving the of shifting the elements cyclically. So if you shift 3 to 6 and if you shift 6 to 12, then you will get a better solution. So basically, if you put 6 over here, if you put 12 over there, you'll get a better solution if you move the numbers backwards by some factor. So we'll try to do a similar thing over here. So instead of making, so case one is in which you put p of x to equal n. So p of x is equal to n. So this basically means that p of 2 is equal to 54, and you're done. You don't need to do anything else. This is one possibility, but this is not the minimal possibility. There are other possibilities. The other case is in which you do p of x times some value, p of x times in this case times 3 works. In general, it will be p of x times some k, such that this number divides n. Let me explain with the help of this example because it may not be very clear. So over here, it's possible that you said, so p of x is equal to some multiple. So if you consider the prime factorization of 54, you will notice that 54 is 2 times 3 cubed, and if you go backwards from 54, if you consider the factors of 54 backwards, then you'll realize that uh, when you're going backwards, it's going to be 27, 9, 3, and 1. And we actually want to go from n to x. So we want to go from 2 to 54. So 2 times 3 is 6, 6 times 3 is 18, and 18 times 3 is 54. This is equal to x and this is equal to n. And this representation helps us, going from x to n helps us, because we know that we can, one possibility is just letting these two positions be the same, but the other possibility is in which you set p of, the optimal possibility is in which you set p of 2 to be equal to 6, p of 6 to be equal to 18, p of 18 to be equal to 54, and this is the best way to, this is the optimal and lexicographically minimal permutation, because you can see that p of 2 is minimized. So basically what I'm saying is that p of x should be equal to p of x times the smallest prime factor of n by x, or if you want to simplify it even further, you consider the factors of n by x, because that's what we are doing over here. When we are going from x to n, we are basically finding factors of n by x. So if you take n by x, in the first example, when you take n by x, you get 12 by 3, which is 4. So 12 by 3, which is 4, is 2 into 2. So that's why you go from 3 to 6 to 12, 2 into 2. Over here, if you consider factors of n by x, so 54 by 2 is 27. So that's 3 into 3 into 3. So that's why you go 2 times 3, which is 6, times 3, which is 18, times 3, which is 54. And you shift the numbers one ahead. So you set p of 2 to be equal to the p of 2 times the factor. You set p of 6 to be the next number, and you set p of 18 to be the next number. And in this way, you can form a kind of cycle so it's not exactly a cycle, it's more like a line of numbers, such that each number is assigned the next number, and The and the reason why this works is because we know that one p of 1 is already equal to x, and we just need to ensure that something comes at position x and the number n goes somewhere. So we know that if something should come at position x and if the number n should go somewhere, you can find a path from x to n. And if you want to find a path from x to n which has the minimum values for p of x, you will basically find the factors of n by x, and each time you will multiply by the smallest factor. So you'll multiply by 333, or if it was something like 3 to 54, you'll multiply by 2 first, 3 to 6, then 6 times 3 is 18, and then 18 times 3 is 54. So first you'll multiply by 2, then you'll multiply by 3, and then by 3. So each time you want to find the minimum values, and over here you'll set p of 3 to be equal to 6, p of 6 to be equal to 18, and p of 18 to be equal to 54, because we want to ensure that the smallest number comes first and the largest number comes in the end. And uh, now I'll show you the code which implements the same idea. And you should pause the video if you didn't get the approach fully, and maybe try a few examples on your own, because number theory problems like this are all about working with numbers and trying out various examples and seeing patterns, and you can understand that by yourself. I try to explain it to the best way I could. So in the code for each test case, I taken the value of n and x. As I mentioned, we want to go from x to n. We want to reach x to n, and that's why we need n to be a multiple of x. Either n is a direct multiple of x, or we go from x to some multiple of x to some other multiple of that multiple, and we keep on going along the line until we reach n eventually. So even in that case, we know that n should be a multiple of x. So if n percentage x is not equal to 0, we print -1. In all the other cases, we know that there's going to be some answer. So for that, we find the prime factorization. So this stores the prime factors of n by x in ascending order. Another way you could do this is you could go from x manually up till n, but I choose to find the prime factorization, and using the prime factorization, I store the values. So I store the next values for each element I going from 1 to n. So next value of I is equal to 0 if I is not in the line from x to n. Otherwise, it is equal to the next value. So it is equal to the next value in the line after I. So for example, next value of I will give you the multiple which you need to put in position I. So it signifies the element that must appear at position I. So for example, next value of 3 will be equal to 6, next value of 6 will be equal to 18, and next value of 18 will be equal to 54, because P of 18 is 54, and from 18 you go to 54. So that's the next element that you'll go when you're traversing the line from x to n. So we store all these elements. We store all these elements in next val, and we basically iterate through all the prime factors and keep multiplying the current element by the current prime factor. So and set the next value of the current element to be the next element in the list of prime factors. So we know that the loop will end at the end, car will be equal to n. So we can just do an assert car is equal to n, because we know that because we reach n from x eventually, because these are a finite set of prime factors, and once we do this, we know that we have successfully placed the number n at some position, and we have successfully placed some number at the position x. So both the number and the position are assigned, and because we are starting from the position x and we are reaching the number n, so we are basically we want to reach number n from position x, and we can do that only by going to the multiples of x. So that's why we need n to be a multiple of x, and we know that we want to find the smallest permutation. That's why we find the prime factors, which will store the smallest number which we can go to after x, and so we keep going to the smallest number from x. That's why we want to find the smallest multiple of x such that it still divides n, and that's why we do this loop of going through all the prime factors in ascending order and keep on multiplying the current number by the prime factor until you reach n. And once you reach n, we have all the elements of the array. So we know that if is of cur basically represents if cur is part of the line from x to n, and if is of I, you will print next value of I. In all the other cases, we know that the values are set. So p of 1 is equal to x, p of I. So if I is equal to n, um, we can take care of the border case. We already know in these two border cases what are the values of p of 1 and p of n. So we print that. Otherwise, we know that if cur is part of the line, this means that we print next value of I. Otherwise, we know that p of I is equal to I because no other multiple of I is free. So because there's no other free multiple of I, we need to print I. That's the only possibility. However, the reason why we can go from x to n is because n is freed up and we can shift n to a smaller element. In this case, it's a multiple of x. So that's why we can make sure that all the elements in the line have a different number other than their position. But for all the positions which are not part of the line, we have to set them to be equal to I because there are no multiples of I which are not assigned to some other position. And you can verify that this code does get accepted. So I hope you like this solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.